Hello everyone, welcome back to the RAG Mastery Playbook. This is section 5, Top-K Retrieval and Ranking. In this video, we will understand how modern RAG systems find the right information, rank it and improve answer quality through re-ranking and use techniques such as BM25, hybrid search, MMR, Bi-Encoders and Cross-Encoders. We will also see how all of this come together inside the production grade RAG architecture. But before we begin, a quick thought. We all spend time consuming content every day. If you can invest the next 15 to 20 minutes understanding a concept that sits at the heart of modern AI system, it could be one of the most valuable investment you can make in your AI learning journey. So let's make this next few minutes count. Let's begin. Let's start with chapter 1. The problem retrieval is trying to solve. Imagine your company has 10 years of HR documents, leave policies, travel policies, compensation policies, insurance documents, employee handbooks, thousands of pages of information. Now an employee opens the company's AI assistant and asks, "Can I carry forward unused leave to next year, and what is the maximum limit?" The answer exists somewhere inside these documents. But here is the challenge. The AI cannot read thousands of documents every time somebody asks a question. That would be really slow, expensive and completely impractical. So the system needs a way to identify which documents are most relevant before the LLM ever starts generating an answer. This process is called retrieval. Now let's understand what is Top-K retrieval. Let's say the knowledge base contains 10,000 document chunks. The employee asks, "Can I carry forward unused leave to next year?" The retrieval system searches through all available chunks and identifies the most relevant candidate. For example, leave carryover policy, annual leave policy, HR handbook, leave encashment policy, leave policy update. This became the top result. This is called Top-K retrieval. The word top means the most relevant, and the letter K simply represents the number of results it has returned. If K equals to 5, we return 5 result. If K equals to 10, we return 10 result. If K equals to 20, we return 20 results. The AI never sees all 10,000 chunks. It only sees the selected top K candidates. The obvious question now becomes, how does the system decide which chunks are relevant? To answer that question, we need to understand embeddings. Computers cannot directly understand language. They convert text into numerical representation called embeddings. Every document chunk is converted into an embedding. Every user query is also converted into an embedding. Think of embeddings as coordinates in a massive multidimensional space. Documents discussing the similar topics are located close together, and documents discussing unrelated topics are located far apart. When the employee asks, "Can I carry forward unused leave to next year?" the question is converted into an embedding. The system then searches for document embeddings that are closest to this query embedding. Each document receives a similarity score. For example, leave carryover policy, annual leave policy, HR handbook, insurance policy, all this receives a similarity score. The higher the score, the more semantically similar the document is to the query. One of the most common technique here we use is called cosine similarity. Now, without going into the mathematics, cosine is something which measures how closely two vectors point to the same direction. Higher similarity, higher score. Lower similarity, lower score. At this point, many people may assume that the highest similarity score must always be the best answer. but that's where things become more interesting. Now let's switch example for a moment. Suppose a user asks, how do I reset my password? The retrieval system returns password policy, password reset guide, password expiry rules, password security standard. Similarity score are also different values for password policy, password reset guide, password expiry rules. Now at first glance, password policy may be appearing to you as the best result, but as human we know something is wrong. The user is not asking about policy, the user wants instruction for resetting a password. The actual answer exists inside the password reset guide. This is where ranking comes into play. A similarity score answers how similar is this document to the query. The ranking score answer how likely is this document to answer user question. So these are two completely different things, and this distinction is one of the most important concepts in retrieval-augmented generation. Now we will learn why retrieval alone is not enough. Similarity search is incredibly powerful, but that is not perfect. A document can have a very high similarity score but still fail to answer user question. Why? Because similarity measures relatedness, not answer quality, not user intent, not usefulness. That is why modern production systems rarely stop at retrieval. They add a second stage, re-ranking. Now let's understand what is re-ranking. Think about hiring. 500 resumes arrive for a role. Do you interview all 500 candidates? Of course not. First you perform a quick screening. Maybe 20 candidates are shortlisted. Then you evaluate those 20 in much greater detail. Finally, you select the best few. Modern RAG systems work exactly the same way. Step 1. Retrieve 20 potentially relevant chunks. Fast, efficient, but approximate. Stage 2. Analyze those 20 chunks more carefully. Re-rank them. Keep only the best 5, accurate, focused, and useful. Only those final chunks are then sent to LLM. This two-stage design helps us both speed and with quality. Now let's understand Bi-Encoder versus Cross-Encoder. We need to understand how this works technically. The first stage is usually performed using a Bi-Encoder. In a Bi-Encoder architecture, the query is encoded separately. The document is encoded separately. Then two embeddings are compared later. This approach is extremely fast. It can search millions of chunks, but there is a limitation. The query and the document never interact directly while being encoded. This is where cross-encoders comes in. A cross-encoder processes the query and the document together as a single input. This allows the model to understand the relationship between the question and the document much more accurately. But the trade-off is speed. Cross-encoders are slower, so production system uses a combination. Bi-encoders retrieves top 20, cross-encoders re-rank those top 20. Top 5 then go to LLM. This architecture has become the standard pattern for enterprise RAG system. Now we will understand BM25 and exact keyword search. Let's look at another challenge. Suppose someone searches for leave carryover limit or policy section 402 or some error code. In this situation, exact words matter. Semantic similarity alone may not be sufficient. This is where BM25 becomes valuable. BM25 is a traditional keyword-based ranking algorithm. It rewards documents containing exact search item. Unlike vector search, BM25 does not understand meaning. It focuses on word frequency and word importance. For exact phrases, product codes, policy references, legal clauses, and technical identifiers, BM25 can sometimes outperform semantic search. Now let's talk about hybrid search. So which approach should we use, vector search or BM25? In production system, the answer is often both. Vector search understand meaning and BM25 understand exact terms. Hybrid search combines both approaches. The retrieval system runs vector search as well as BM25 in parallel. The results are merged into a unified ranking. This gives us the strength of both worlds, semantic understanding and exact matching. This is why hybrid retrieval has become a common pattern in enterprise AI system. Now it's time to understand MMR and the redundancy problem. Let's assume our retrieval system returns 5 chunks. Unfortunately, all 5 chunks come from the same leaf policy chapter. They contain nearly identical information. The LLM receives repetitive context. Most important information from another relevant documents often get ignored. This is called the redundancy problem. The solution is MMR, maximal marginal relevance. MMR tries to balance two objectives, relevance and the diversity. Instead of selecting 5 highly similar chunks, MMR selects chunks that are relevant while also contributing new information. The result is richer and more balanced context for the LLM. Now let's bring everything together. Employee asks, can I carry forward unused leave to next year? And what is the maximum limit? Then step 1 will be the query is converted into an embedding. Step 2, vector search and BM25 run simultaneously. Step 3 is the system now retrieves the top 20 candidate chunks. Step 4, a cross-encoder re-ranks those 20 chunks. And then step 5, MMR removes redundant chunks. Step 6, the final top 5 chunks are selected. And then in the next step, those chunks are sent to LLM. Step 8 will be the LLM generates the final answer. Now you notice something important. The LLM did not magically know the answer. The retrieval pipeline found the answer. The LLM simply synthesized and presented it. That is how production grade RAG system work. Now let's quickly recap what we have learnt in this chapter. We explored how Top-K retrieval finds the best document candidate, how ranking improves answer quality, and how Bi-Encoders and Cross-Encoders balance speed with accuracy. We have also learned how BM25 hybrid search MMR work together to build better context before the LLM generates a response. And remember, the most important takeaway is this: the LLM does not know what information to go. It is the sole responsibility of the retrieval part. And with that, we have reached the end of RAG Mastery Playbook. Together, we have explored the complete RAG journey from understanding why RAG is needed to document ingestion, chunking, embeddings, vector databases, and finally, how modern systems retrieve, rank, refine information before an LLM generates an answer. I hope this series has helped you to build a very strong foundation in Retrieval-Augmented Generation. Thank you for learning with us. This is EdgeTalks, clarity that moves with you. I see you in the next episode.